Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 4, Lesson 5 on similar figures. Now, kind of a little spoiler, the whole point of working with dilations in the first place, the whole point is to get to similar figures. So, we talked in, a couple units ago about congruent figures, and congruent figures are two figures that are just identical. They're just the same, right? They're the same size, they're the same shape. That's what they are. Similar figures are literally two figures that are the same shape, but they're not the same size. So again, you take a picture with your phone camera and you expand it to make it larger, you might say it's the same image, but it really isn't, right? But it looks the same, relatively speaking, because all you've done is either made it larger or made it smaller. So let's kind of get in and formally define what a similar figure is. All right, here we are. Congruent figures are identical in both shape and size. They are created by those rigid motions, translations, reflections, rotations. But figures that are created by dilations are called similar. And we're going to kind of explore them today, go through them, understand kind of the ideas behind them, and then work with them quite a bit in the next few lessons. Let's get right into it with exercise number 1. In the diagram below, triangle DEF is the image of triangle ABC after a dilation by a scaling factor of 2, our favorite scaling factor. Letter A, using a straight edge, find the center of dilation and mark it as point G. All right, well, why don't you go ahead and do that? Using a straight edge, and you're going to also need a ruler measured in centimeters, so you might as well have them both. See if you can locate the center of dilation. All right, well, we've only done this once before, but remember, right? Wherever the center of dilation is, it's got to lie somewhere along the line that connects A and D. Given that D is the image of point A, then somewhere in that direction the center's got to be. But likewise, the center would also have to lie along the line that connects F and C, and along the line that connects B and E. So we can use that fact actually to identify where the center is. So here we go. I'm going to take my ruler and I'm going to draw a nice straight line or ray or segment or whatever you want to call it from D through A. All right, somewhere the center lies along that. I'm going to do the same thing for point C and point F, and again, hopefully for you this is a little bit easier. My ruler is a bit more cumbersome than yours, right? And since the center has to lie somewhere on both of those line segments, that means the center must be right there. Oh, no, I want to mark it as point G, not point E. Now, one way to verify that that's the center is use the last set of points that we haven't used yet. In other words, does that center also go through B and E? And the answer is yes. We don't really have to draw that last one in, right? This last one really isn't necessary, all right? But it's kind of a nice verification that that is in fact our center. Isn't it kind of cool? This almost has this like three-dimensional look to it now, which is kind of cool. Anyway, let's take a look at letter B. Letter B says, measure the lengths of the sides of both triangles to the nearest tenth of a centimeter. All right, so take your ruler out as carefully as you can. Measure the lengths of all the sides, all 6 sides, 3 of these, and see what you get. Again, to the nearest tenth of a centimeter. All right, well, let's go through it. Easy enough. Of course, we've got a ton of stuff sitting here now. I'm going to shrink this down a bit, but let's take a look. For AC, we've got a length of, looks like, and these might be a little bit different for you than they are for me, but it looks like we've got 3.5 centimeters for AC. It looks like for AB, we've got 5 centimeters. Sorry, that was for BC, not AB. And then for AB, which is being particularly tricky for me, we've got 4 centimeters. All right, now let's come over and do the same thing for the larger image triangle. For FD, it looks like we are just about at 7 centimeters. All right. For FE, it appears that we're ringing in right in at 10 centimeters. And for DE, all right, it looks like we are right about at 8 centimeters. Now, your measurements might be slightly different depending on how these worksheets got shrunk or expanded, how the worksheets themselves got dilated. All right, but according to my measurements, we have 3.5, 5, and 4, 7, 10, and 8. All right. Now, exercise number 2, we're going to keep on the same sheet because it links into exercise number 1, so let's take a look. Using your diagram in exercise number 1, state the value of each of the following ratios of lengths. Write the ratios and then simplify. They should all turn out nice. All right, well, why don't you go ahead and do this? Like, now that we've got those measurements, you can literally set up each one of these ratios, and if you need to use your calculator, go ahead. I'm going to need it for a little bit of algebra that I do later on in the lesson, so I've got it kind of open and waiting. But these should turn out nice. You probably shouldn't need to use it. Why don't you go ahead and pause the video now? All right, let's take a look. EF divided by BC. Well, let's see. EF is 10, BC is 5. So we've got 10 divided by 5, and that, of course, reduces to a ratio of 2. DE divided by AB. DE is 8, AB is 4. So we have 8 divided by 4, and of course 8 divided by 4 is 2. And let's see. DF divided by AC. That's going to be 7 divided by 3.5. That's maybe the only challenging one, but that is 2 as well. Now, we shouldn't be surprised at all these ratios. In every single one of them, we had an image line segment divided by a pre-image line segment, right? So the image divided by the original, etc. And in each case, we found that the image was twice as large as the original. And of course it was. I told you up front that this was a dilation with a scaling constant of 2. And that's what the scaling constant does. Sure, it moves all points twice as far, from the center as where they started, but it also makes every single line segment twice as long as what it originally was, again, for a scale factor of 2. Let's keep going. All right, so corresponding sides of similar triangles are proportional, meaning that their ratios always have that constant value, and that constant value is equal to whatever the dilation constant is. Now, corresponding sides, that's an interesting term that you're going to see a lot of in sort of future lessons and in future years. Corresponding sides mean sides that are sort of in the same place on two different triangles. So, right, if I go back to the previous exercise, side AC and side DF are corresponding sides. They're, if you will, the left side of both of these triangles. BC and EF are corresponding sides because they're both the sides that are sort of at the bottom of the triangle. And, we could keep going on. But the point is, corresponding sides are proportional, meaning that when we do the ratio of two corresponding sides, it will always be equal, and it'll be equal to the scaling constant. Let's keep going with exercise number 3. All right, exercise 3. The angles of the two figures, or of two similar figures above, also have a special relationship. Letter A asks us to trace triangle ABC onto tracing paper and use this to compare its angles to those of its image triangle ABC. It actually should be its image triangle DEF. All right? So, why don't you go ahead and do that? Trace out triangle ABC and then compare its angles to the angles of triangle DEF to see if they've also been scaled by a factor of 2. Wouldn't it make sense? I mean, all the side lengths have been scaled by a factor of 2. One might think that the angles are twice as big as well. Pause the video now and see if you can figure out if that's true. All right, well, angle A corresponds to angle D. So let's just try that one, right? If I, move my tracing paper over here, well, was this angle twice as big as this angle? No, in fact, those two angles are identical, right? Angles aren't about the length of the rays that are coming out of the vertex, because those rays extend forever. It's really about the rotation between the two rays. And since these rays overlap these rays, the angles are the same. Let's see about angle C and angle F, right? For that, I can just bring this triangle right down here, and looks like that's also equal. And it looks like that's also equal. So the answer there is absolutely no. The angles were not scaled by a factor of 2. And by the way, you probably could realize right from the get-go that the answer would have to be no, because the sum of the angles of a triangle are 180 degrees always for any triangle. So if these angles had actually gotten to be twice as big as these angles, then if these summed to 180, these would have had to sum to twice 180, which is 360. And then that would mean we'd suddenly find a triangle where the angles don't add up to 180 degrees. So the angle is no, right? So what can we say about the corresponding angles in a figure that is the image of another after a dilation? Well, we can say that they're congruent, right? The corresponding angles in two similar figures are congruent. Or you could also say that they're equal in measure. So the sides, right, the sides of similar triangles, or similar figures in general, get scaled by the same amount that the scaling factor is, but the angles stay the same. And this is why we say that two figures that are similar have the same shape, those are the angles, but a different size. Let's summarize all of this, right? Similar figures. If two figures are similar, then their corresponding sides are proportional and their corresponding angles are congruent. And we use this funny little symbol. Let me draw it a little bit bigger. This symbol, all right, to formally show that two figures are similar. Okay, and you may have seen that before. That symbol was the one that sat above the equal sign when we were showing or claiming that two figures were congruent, right? Because what congruency really is it's kind of like the equality teamed up with the similarity, all right? But similarity, this symbol, just means that two figures will have the same angles, but their sides will be scaled from one another, right? All the sides will be twice as big or 3 times as big or half as big or 1/3 as big, all right? Let me get rid of these two things. So let's work with that idea in exercise number 4. In the following diagram, triangle KLM is similar to triangle QRS. The diagram is not drawn to scale. Letter A, list the congruent angle pairs between the two figures. Use tracing paper to verify that the angles have equal measures. All right, so go ahead and list the congruent angle pairs and trace out triangle KLM onto a piece of tracing paper, and then do what we did in the last exercise to really verify that, yeah, those angles sort of fit with one another. Pause the video now. Well, the tracing paper can actually kind of help you a little bit in terms of what angle is congruent to what. So if I bring this over, right, I can see, yeah, there we go, look at that. And by the way, notice every time I do this and I kind of nestle one triangle inside of another, doesn't it look an awful lot like those dilation diagrams where we had a center and a line segment and then we kind of dilated it out to a new line segment? I mean, isn't that almost essentially what this picture is? All right, you'll see that again and again and again in similarity work. So let me just delete that. So what can I say? I can say angle K is congruent to angle Q, right? That's one congruent pair. I could nestle it down this way. That would tell me that angle L is congruent to angle R. And likewise, I could bring it out to here, and that would tell me that angle M corresponds and is congruent to angle S. All right, let's take a look at letter B. What is the scaling factor needed to map triangle KLM onto triangle QRS using a dilation? All right, so what exactly is the scaling factor that takes this triangle and makes it into that one? This one should be pretty easy. Pause the video now and see if you can figure this out. All right, well, it's really this simple, right? If we look at KL, which is the corresponding side to QR, it's pretty easy to see that QR being 12, KL being 3, means that the scaling factor is equal to 4. All right, now, if that's not obvious to you, all you really have to do is say something like this. You can say, well, I mean, I'm going to take 3, multiply it times the scaling factor, and that's got to be equal to that 12, right? This side and this side, which I don't quite get all in the video, those two sides are corresponding. But then that allows me to just say, all right, I've got 12 divided by 3, so my scaling factor must be 4. Every side length in the bigger triangle must be 4 times the side lengths of the smaller triangle. And then that makes letter C a piece of cake. Fill in the missing sides of triangle QRS using your answer to B. All right, well, easy enough, right? Because the two missing sides, let me get rid of my little red triangle here, the two missing sides of triangle QRS are simply going to be 4 times the corresponding sides over here. So this thing is 4, 4 times 4 will make that side equal to 16. Likewise, right, this side's 5, 4 times 5 will make that side equal to 20. And again, all I'm doing is scaling this triangle so that all side lengths are 4 times the side length of that triangle, but all the angles remain the same. All right, let's keep going on this. Oh, actually, yeah, I guess I could have just filled them in right there. Let's keep moving. Here we go. Now, in the last problem, that scaling factor was equal to 4. So it was kind of a piece of cake. You know, we literally just were like, all right, 4 times this, 4 times that. But let's look at a situation where algebra can actually help us find the missing sides of similar triangles. Exercise number 5. In the diagram shown below, triangle ABC is similar to triangle DEF. Letter A asks us to set up and solve a proportion to find the value of x. All right, so just for a second, right, here's x, right? And x corresponds, or x is the length of side DE, and that corresponds to side AB, right? So those two sides correspond to each other. What we really want is we want two sides that are known between the two triangles, and that happens to be these two sides. Okay, now at no point in time in this problem do we claim that this one is this one after a dilation or vice versa. So I'm not going to figure out any scaling constant here, although I could if I just said one of them was the image of the other. I could figure out a k value, but I'm not going to even do that. What I'm going to do is something like this. I know if I take this side and I divide it by that side, so if I take 12 and I divide it by 18, right? So 12 divided by 18 has to be the same ratio as x divided by 9. That's what it means for variables to be proportional to one another, or for the side lengths to be proportional to one another. Now this is where it's kind of nice when I solve this using some cross multiplication. This is where it's nice to just have the calculator so you don't have to do any of the multiplication or division sort of in your head or on paper or anything like that, right? We can just do some cross multiplying here, and we're going to get 18 times x, which is 18x, and then we're going to get 12 times 9, which I suppose I should know in my head, is 108. And then the beauty is we just need to divide both sides by 18, and we're going to find x is equal to 108 divided by 18, x is equal to 6. All right, simple as that. Letter B. Set up and solve a proportion to find the value of y. All right, well, this is basically identical to letter A, so why don't you pause the video and see if you can set up a proportion and find the value of y. All right, well, I'm going to continue to use my 12 and my 18, but technically speaking, you could use your 6 and your 9 now. So I'm going to say, all right, 12 divided by 18, right, 12 divided by 18 must be equal to y divided by 12. Right? Again, I'm going to do a little bit of cross multiplication. All right, so I get 18 times y is equal to 12 times 12. That one I just know off the top of my head is 144. And now I can do 144 divided by 18 gives me y equals 8. All right. Now, let's look at one more pretty important thing, and we're going to really get into this in the next lesson, but I like to start looking at it in this lesson. Letter C. In triangle ABC, side BC is twice the length of side AB. Certainly the case. Is this true for their corresponding sides in triangle DEF? So, kind of note, right? Side BC, which is 18, is twice the length of side AB, which is 9. Does that relationship also hold when we go over to triangle DEF, which is similar to it? Take a look at that. And the answer is yes, because EF, which is 12, is twice DE, which is 6. And again, we'll kind of really harp on that next time, but we're going to say yes because EF is twice DE. Yeah. And by the way, that will definitely always happen. We'll call that the ratio of relatively positioned sides in the next lesson, which is a little bit confusing because it seems a lot like the ratio of corresponding sides, but not quite the same thing. All right, let's wrap this up. One of the most important ideas in geometry is this idea of similar figures, right? And all similar figures are figures that have been dilated, which just means they've been enlarged or shrunk by a particular dilation constant from another figure. And those figures have these properties where all of their side lengths, the corresponding side lengths, are proportional to one another, and all of the angles are the same. Because as soon as the angles get to be different, then the figure fundamentally looks different. It's not just bigger or smaller, it's got a different shape, right? And then those figures wouldn't be similar. So when we dilate one figure, and again, triangles are just a great example of them. When we dilate one triangle, let's say with a factor of 2, then we get another triangle whose side lengths are always twice as long, but whose angles are identical to the original. All right, we're going to be obviously looking at this more in the next lesson. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.